was a grade 12, so we are now going on to inverse graphs. Okay, and all I've done here, guys, just to save space in that, is I've printed 2 slides per page. Okay, so that's one slide, etc. Okay, so as we start here, it says the inverse of a function reverses the process of the function. Okay, the inverse of any function is the reflection of the function in the y is equal to x. Please highlight that, that's important. Determine the inverse of a function. To determine it, we change the x and the y. And you guys will see in an example how I do that, okay? The domain of the function becomes the range of the inverse, and the range of the function becomes the domain of the inverse. So basically, you're just swapping the x and the y, okay? And you'll see in a second how we do that. Right, the next thing, if this f is a function, to denote the inverse, it's f to the minus 1. Okay, so that's just notation. Right, so it says here a function h doubles the input value and then subtracts 1. Describe in words what the inverse does. Okay, so I'm going to reverse it. I'm going to go backwards. So if we subtract 1, then we need to add 1. Then, so we subtracted, then we added. But then, if we double something, that means 2 times. So what we need to do now is we need to divide by 2. So all we're doing is we're just doing the reverse process of the original function, okay? Determine the equations of h and h inverse, okay? So here we've got the original, which is h of x, and what it does is it doubles an input. So 2 times x, which is our input, then it subtracts 1, and that is our original function. Now, what they're talking about here, to determine the inverse of a function, we interchange x and y. How I can rewrite this function is y is equal to 2x minus 1. It's the same thing. Just remember why we use functional notation is just so that we can differentiate between more than one function. Okay? And what I'm going to do now is I'm going to change the x and the y. So if I had to write that, xy is now going to be mapped to yx. So the x maps to y, the y maps to x. Okay, and I'm working with this one over here. So what does the y change to? Well, y goes to x, so that now becomes an x equals 2. What does the x map to? X maps to y, so that changes to a y. Minus 1. Okay, now we never leave an equation x is equal to. So what I have to do is get the y on its own. So I'm just going to take this to that side, and we get 2y is equal to x plus 1. Then I need to divide by 2. So we get y is equal to x plus 1 all over 2. But they want it in this notation like this. So that means that h inverse of x is equal to x plus 1 over 2. Now let's just go back to what we said here. We add 1 to the input, and then we divide by 2. Divide by 2. Okay. Going on to the next one. We have to show that h of h inverse is equal to h inverse of h of x, which is equal to x. Okay, now just remember that our h of x was equal to, I just need to get it there, guys. Our h of x is 2x minus 1. And our h inverse of x was equal to x plus 1 over 2. Okay, so what I'm going to do first is I'm going to test this one over here. So I am going to, what this is saying, I'm going to plug H inverse into H. Plug H inverse into H. So wherever I see an X in H, I'm going to replace it with this. So we get 2. Now the X becomes this. X plus 1 over 2 minus 1. Okay. So over here, the 2's will cancel, and we just left with X plus 1 minus 1. And that is equal to X. Okay. So that is good. We've got this bit is equal to X. Now, over here, I'm going to plug H of X, this one, into H inverse. So wherever I see an X in H inverse, I'm going to replace it with this. So over here, we've got 2x minus 1, because I'm replacing that x with this, plus 1, all over 2. So the 1's will cancel, because minus 1 plus 1 is 0, and we're left with 2x over 2. The 2's will cancel, and we're left with x. So therefore, I've shown now this one is equal to x, and they are both equal to x. Okay, so important, if h inverse hx is equal to x, then the functions are inverses. This is an algebraic way to prove that two functions are inverses. Now, if you take maths into tertiary level, you will talk about injective and surjective functions, which you'll use something like this. Okay, then sketch h and h inverse on the same set of axes. So I need to plot this one, and I need to plot this one. So if I make x 0, we get y is 1, minus 1, sorry. Then if I make y 0, we get x is equal to a half. Just basically plotting a straight line, guys. So here's my h graph. So that's h of x. Now what we need to do is we need to plot this one. So if I make x 0, we get a half. And then if I make y 0, we multiply that up by that, we get 0. So x is equal to minus 1. And there's our inverse function. Okay, now there's a couple of things that I want you guys to pick up from this. First of all, have a look here. For this one, our y was minus 1, but for the inverse, our x becomes minus 1. Now you remember what happened here is our x became y and our y became x. So this becomes that one. Then if we have a look over here for the original, we have a half, but now it's cutting the y-axis at a half. So you see how our values flip around. Another thing that I want you guys to notice here is that these things are symmetrical about this line y is equal to x. They are mirror images about y is equal to x because we are reflecting them about that line. Okay, so those are the three things that I want you to pick up from that. Okay, if I have a look at example 2, a function g squares and then doubles the input. Describe in words what the inverse does. Well, if we double the input, then we are going to divide by 2. Is the reverse of that. So divide by 2. And then what do? We square it. So the opposite of square, then we take the square root. Is the opposite. Okay, determine the equations of g and its inverse. The notation g inverse cannot be used to write the inverse of a parabola as the inverse is not a function. So let's just see what they mean by that. So first of all, let's have a look at what g of x is. So what we do is it squares and then doubles the input. So if we square an input and then we double it. So that is your G. Let's have a look now at what the inverse would be. So remember, what we can do is we can say y is equal to 2x squared. And what we're going to do is we're going to change the x to a y and the y to an x. So this will become x is equal to 2y squared. Okay. To get the y on its own, I'm going to divide by 2. So we get y squared is equal to x over 2. Now I take the square root. So y is equal to x over 2 in the square root. But remember, it's plus or minus, guys, whenever you take the square root. Okay. Now, before I explain why this is not a function, I think it's better if I plot it, and then you'll see what is going on here. Okay, so sketch G, and then its inverse on the same set of axes. So if we look at G, which is this one over here, I'm just going to get some points here. If I put 1 in here, we will just get 2. If I put minus 1 in there, we'll get 2. If I put 0 in there, we'll get 0. So this will be a parabola going like this. Okay, so that is G of x. Now, let's have a look at what this inverse is going to look like. All right. Remember that we're going to flip everything. So this point here was 1, 2. So the other point, if we swap 1 and 2, so it's 1, 2. If we flip that, that's now going to become 2, 1. So 2, 1 is over there. So that point has come over there. If I look at this point here, minus 1, 2. So minus 1, 2. If we flip that, we're going to get 2 minus 1. So 2 minus 1. And that's over there. And then this point here, 0, 0. If we flip it, it's still going to be 0, 0. So this graph is going to look like this. Okay. And again, you can see that this is symmetrical about the line y is equal to x. Okay, so y is equal to x. Now, the reason why over here I'm not going to say, for example, g inverse of x equals this thing is because this is not a function. Okay, and how do we test that? Is with the vertical line. And as you can see here, it's cutting the graph twice. Okay, and that is why it is not a function. So a parabola is a function, you can see that, but its inverse is not a function. Okay, so a parabola is a function, but the inverse of a parabola is not a function. Okay, so let's have a look at the domain and the range here. So for G, the domain is we can have any x values. The range, we read from bottom to top, so it's going to go from 0 up to infinity. Infinity excluded, the 0 is included because it's on our graph. Now, if we look at the domain and the range for the inverse, let's just say that it was a function, we can now see that the domain of this would be from 0, from left to right, would be from 0 to infinity. Okay, that's included, that's excluded. Then the range, you can see that we can have any y values because it's just going to start opening up. So y is an element of the reals. Now, that's what they were talking about initially over here, where the domain of the function becomes the range of the inverse, and the range of the function becomes the domain of the inverse. So if we have a look at the domain for our function, have a look at the domain has now become the range, okay, for the inverse. Then the range has now become the domain for the other one. And you see how they flip around like that. And that's what that statement was saying. Okay. Going on to the next one. It's saying here, explain why the inverse of G is not a function. Well, it's because we are getting many y values for one x value. So an x value is being mapped to more than one y value, okay? And that is y. Then it says here, restrict the domain of G so that its inverse is a function. So if I have a look back at G here, I'm going to be looking at the turning point. Now, how I would restrict this so that the inverse is a function is I would have a look at where x is greater or equal to 0. So this arm over here would now be mapped to this arm over here. So let me highlight that for you guys. If I restrict it just from 0 onwards, you can see that this arm will be mapped to this arm. Only that arm. And I'm only plotting that green bit. Now you can see that this arm here is a function because it's cutting the graph only once. Then, if I restrict this part from less than 0, so just this arm over here, this arm will be mapped to this bit here. Okay, and you can see with that red bit, that is a function. Okay, so how would we restrict this? Well, I would say x greater or equal to 0. So that was for the, just want to get the colors right here. That was for the green bit. And then the other one I would look at is x less than 0. And that was for the red arms. Okay. Then, restrict the domain of this function f is equal to x plus 1 squared minus 3 so that its inverse is a function. So what they've done here is they've given us, or they've plotted the this function over here. And you can see that this coordinate over here is minus 1 and minus 3. And we can read that off here. We just change the sign of that, minus 1, minus 3. And there it is there. So, having said that from this previous one, how we restricted the domain from the turning point so that the inverse is a function, I'm going to do exactly the same here. So it's always with respect to this x value of your turning point. So over here, I would say x greater or equal to minus 1. And the other one is x less than minus 1. So basically it was like this for your green arm and then for the red arm. Okay, and I got it from here, from the x value of the turning point. So if I restrict it like that, then the inverse would be a function because the green bit would be this arm here. And if we flip that, that would be an inverse. And then we've got the red bit over here. If we flip that, that would be a function. Okay, grade 12, so you can do exercise 2.2, numbers 1, 2, and 3 for me on this work. I just want to finish this off. Okay, so we've just got this last bit here. So here it's example 4. It says, is the graph a function or not? Well, is this a function? We'll take the vertical line test, and you can see that the ruler is cutting the graph only once. So yes, this is a function. Then sketch the inverse of this graph. So I'm looking at critical points here, guys. So 0, 0 is a critical point. If I had to flip 0, 0, it would just be 0, 0. So my inverse is going to go through there. The next point I'm going to look at is this one over here, which is 1, 4. If I had to flip 1, 4, it would go 4, 1. Okay, so that is going to go 4, 1, which is over there. The next one I'm going to look at is this one is 3, 0. If I have to flip that, that would be 0, 3. So 0, 3 is going to be over there. Okay, now how is this graph going to look? Well, first of all, this 1, 4 bit was a turning point, so that 4, 1 will be a turning point. So we know it's going to go through here. It's going to turn here, come here, turn at this point, and then it's going to shoot off again like that. Okay, So there is your inverse. All right. So we've sketched that. Then, is the inverse a function? Well, let's have a look at the vertical line test. Over here, it's fine. It's cutting once. But then when we get over here, you can see it's cutting 1, 2, 3. 1, 2, 3, 1, 2, 3. So it's not a function. So this is no. Okay. So guys, that's how I would do that. Just get your critical points and then you can just draw them, okay? Now for this, I would do exercise 2.3, numbers 1, 2, and 3. You don't have to worry about that, okay? And that is the end of inverses, guys. Thanks.